Okay, now I'll talk further about the dot product with some observations we can make about it. Okay, so let's just look first at the form of the dot product here. So we have, starting with two vectors, u and v. And again, you can write it with the little arrow on top, or not, like I have here in the formula. The dot product between those two vectors is a scalar, so a number, not an ordered list of numbers, that represents the cosine of the angle between them. But let's look what this is. This actually looks familiar from our vectors topic. Right? If we just kind of cut this here, what do we have on these two sides here? Well, I've got u divided by the length of u, and v divided by the length of v. If you remember what that is, this is a unit vector. This is a unit vector, so a vector of length 1, in the direction of u. So what we put into the dot product is really two unit vectors that are pointing in the directions of the vectors that we have. One points in the direction of u, one points in the direction of v. Okay? So this denominator here, what it's doing is taking out the length of those vectors so that we're only dealing with unit vectors. Okay. I'll mention one thing further here, and I'll do it via an example. This is an important property of the dot product. I'll just take two unit vectors. Like this, for example. Now if I were to dot these, remember how this goes is I take the product of the first two numbers plus the product of the second two numbers, like this. You can see that gives me 0. Okay, now this makes sense because if I look at what I should get back from the dot product, I get the cosine of the angle between them. Now what is the angle between u and v? Well, these are the two unit vectors pointing along the coordinate axes. They're at right angles to each other. So the cosine of 45 degrees, or pi over 2, is 0. And that's what exactly I have here. So we make a little observation here. The dot product of two vectors at right angles is 0. And importantly, this works the other way around. So if I have two vectors, I don't know what their angle is between them, I calculate it and I get 0 back, that means those vectors are at right angles to each other. Okay? That's one of the fundamental properties of the dot product. Okay, one further observation about the dot product comes from this here. So we might have two vectors in space like this, and we want to know how much of the vector u is in the direction of v. Okay? This pops up all the time in engineering and science where, for example, you're building a bridge and you want to know how much of the weight of the bridge is present in all of the supports holding up the bridge. Okay? And we can calculate that with the dot product. Let's just notice if I drop this line here, this is at right angles. Okay? So then I could find the length of this side very easily. Again, we just use basic trigonometry. This is the adjacent side to this angle. This is the hypotenuse. So we know that the cosine of the angle between those two is simply just the length of the adjacent side. So maybe I'll call it u sub v. Okay. So this is this side here. Let's make it a little vector. And this is the component of u in the direction v. Okay. So this is just the length of the adjacent side divided by the length of the hypotenuse. And I can rearrange that, just multiply both sides by the length of the hypotenuse, which in this case is just u, like this. And then I have the length here. Okay, I have the length of that vector. But now if I want to find that vector itself, how would I do it? Well, it's in the direction v. It has length this here. So what I could do is take a unit vector. That's the standard multiplication. Maybe I'll write a little cross this time. I could take a unit vector in the direction v, okay, so in this direction, and I can scale it by the length of this vector that I'm trying to find. Okay, so let's do that. I have an expression for the length of that u in the direction of v. It's just the length of u times the cosine of the angle between them times this unit vector. But hold on, I've got a way of calculating this, which doesn't involve trigonometry at all. That's just the dot product of u and v divided by the length of u divided by the length of v. Okay, like this, times this vector, the unit vector in the direction v. Okay, so there's some slight simplification that we have here. The length of u will cross out like this, and what we end up with is this here. This gives us a vector representing the component of this vector u in this direction. So let's do a quick example. Let's say we want to take a vector u, which is 2, 3, and a vector v, which is 4, 0. Okay. Now, before we even set out and calculate this, why don't we just drop down to Desmos and plot these two, just so we can look at the situation, see what it might be, the answer. So this u is a vector from here to this red dot, v's from here to this blue dot. If I want to know how much of that vector u is in this direction, I can just kind of project it down, and I see I should get 2, 0. Right? The length of u in the direction of v is 2. Project it down, I should get this vector, 2, 0. So let's actually do the math and see if that's what we get. Okay, in order to do that, we just need the length of v, which is very simple. It's just 4. We could use the Pythagorean theorem to calculate that, but sure enough, we get 4 back. Okay, so now let's calculate this vector. That's going to be u dotted with v over the length of v multiplied by, you can see there's problems between the dot product and writing multiplication as a dot. The dot product's usually a bigger dot than multiplication, but sometimes it can get a little confusing. Anyhow, let's do the dot product. The dot product is just 2 times 4 plus 3 times 0. Okay, and that's over the length of v, which is 4. And that's multiplied by this vector, 4, 0, over the length of v, which is 4. Okay, and you can calculate that. That's going to be 8 over 2, or sorry, 8 over 4, which will be 2, times, well, 4 over 4. It's just going to be this unit vector in that direction. You can look at what we get. We just have 2 times that vector, which is exactly as we suspected it would be. This. So when I take that vector u in the direction 2, 3, and I want to know how much of that vector is in the direction v, all I do is this, and sure enough, I get this vector, 2, 0. Okay, and we'll do some further practice. I'll leave some up for you to try. You know, it changes things a little bit when you move the vectors away from the horizontal or vertical axes. But the math all works to be the same. Just simply this projection formula right here. Okay.